All right, so now we're going to take a look at the relationship between the Gibbs energy and equilibrium. So what we're going to see here are a couple of things. We're going to try to relate what we just learned about Gibbs free energy to this whole concept of equilibrium that we saw in the previous section. Now, if you think about it, equilibrium is just another word of looking at thermodynamics, and we'll see why it is here in a second. Now, just to relate a couple terms that we saw before, we looked at the magnitude of K, the equilibrium constant, and this that we saw previously is going to be analogous to the sign of delta G under standard conditions. So the magnitude of K is going to give us the same information as the sign of delta G under standard conditions. So what that means is we saw before that a large K value, where K is a lot greater than 1, tells us that this equilibrium, if there's a large K, that means that the equilibrium lies to the right. So mostly products at equilibrium. And this is the same as if we calculate delta G and we find that delta G under certain conditions is a negative value. Okay, so we're making some comparisons between the Gibbs free energy, standard Gibbs free energy, and the magnitude of K, the equilibrium constant. So large K, we know, tells us that the equilibrium lies to the right. At equilibrium, we have mostly products, which is why that K value is large, and that corresponds to a negative delta G under standard conditions. And what this also means then, if we have a small K value, so small K, so a lot less than 1, that tells us then that we have more, or the numerator is small, the denominator is large in our K expression. That means that equilibrium then is going to lie to the left. On the left side, we have mostly reactants. So at equilibrium, we have mostly reactants. If there was a K, a very small K value, and this corresponds to a positive delta G. Okay, so the magnitude of K is going to give us the same information as the sign of delta G. The standard gives the energy with the delta G with the degree sign on it. So remember now, when we talk about delta G, standard, this is under standard conditions. Which for the two most commonly encountered physical states, we have our gases. For example, this is assuming then that they're all in 1 atmosphere. And then for aqueous solutions, the concentrations of these solutions are all assumed to be 1 molar. Now, these are under static conditions. Well, how often are we actually using gases at 1 atmosphere of pressure? And how often are we always using solutions at 1 molar concentration? Well, the answer is very infrequently do we encounter those situations. However, we can calculate these, like we've done previously. We calculate the delta G standard values from data in our tables that we can look up. But this doesn't really highlight the situation or the delta G under real life circumstances. So for example, if you actually perform a reaction in the lab, for instance, are you working under standard conditions? And in most cases, the answer is no. So how then can we determine delta G under non-standard conditions? Which is what we're encountering most of the time. This is a very important question that we need to find the answer to. So our delta G standard tells us complete information as a magnitude of K does. So delta G, if it's negative, tells us the equilibrium lies to the right. Delta G, if it's positive, tells us the equilibrium lies to the left. And again, these are under standard conditions that we're calculating. So if we are starting off with a non-standard condition, what we can do is we can then predict based on the sign of delta G, not delta G standard, we can predict how that reaction is going to proceed. Will it proceed to the right? Will it proceed to the left? Or is it at equilibrium? So the sign of delta G, not delta G standard, is what will determine the spontaneity of a reaction as written. We have a reminder, we saw this previously, if delta G is less than 0, in other words, it's negative, that means the reaction is spontaneous in the forward direction, from left to right, until we establish that equilibrium. If delta G is greater than 0, so delta G is positive, the reaction is non-spontaneous in the forward direction. Which means it's spontaneous in the reverse direction. And it will proceed in that reverse direction until we establish equilibrium. If delta G then is equal to 0, we know that the system is at equilibrium. So the sign of delta G, which is the delta G under whatever the conditions are of our experiment, tells us how that reaction will proceed. Will it proceed left to right? Will it proceed right to left? Or is it already at equilibrium? And we're going to see now the relationship between delta G and delta G standard. So what we're going to see then is if we try to relate delta G under standard conditions to delta G, which is the situation or the conditions that we are working with normally in the lab, for example, the relationship between those two is as follows. So delta G is equal to delta G standard plus the product of the gas constant R times the Kelvin temperature T times the natural log of the reaction quotient, right, which is Q. So what we have is a relationship now that incorporates an equilibrium principle in it. So remember, Q is the reaction quotient, which is nothing more than K, how we write K, the equilibrium expression, under a specific set of conditions. Right? So Q is simply equal to the product raised to whatever the stoichiometric coefficient is divided by the reactants. Okay, so our delta G value, delta G standard, we can calculate this, we can look this up with our data tables. And if we know what the temperature is, and if we know what the concentration are of the products and the reactants at that particular point in the reaction, we can determine delta G for that reaction, and we can predict in which direction that reaction is going to proceed based on the sign of delta G. So let's take a look at an example. And we have here an equilibrium, the gas state equilibrium, hydrogen with iodine, and hydrogen iodide. We are told that the delta G standard for this, our 25 degree, is 2.60 kilojoules per mole. And then we're given the following information. We're given the partial pressure of X, the species. So remember, when we write that Q expression, the equilibrium expression, that can be written in terms of concentration. But if we also have gases present, we can also write them in terms of the partial pressure of the gases. So if these are the information that's given with respect to the pressure, the partial pressure of the reactants and products, and Q, and we'll use a subscript P to represent pressure, it would be the pressure of HI, and then because the stoichiometric coefficient is 2, we're going to square that, divided by the partial pressure of H2, here, and that's raised to the power of 1 times the partial pressure of iodine raised to the power of 1 as well. And I'm just going to substitute those values. So we have 3.0 atmosphere squared for the HI, we have 2 for the H2 and 2 for the I2. So that gives 9/4, which gives us 2.25 as my QT value. So I can then take that and insert it into my delta G equals delta G naught. That's how you would read that, plus RT, natural log of Q. Right, so we substitute these values. Delta G naught there was 2.60 kilojoules per mole, plus R, the gas constant, 8.314 times 10 to the minus 3 kilojoules per mole, kilojoules per Kelvin mole, sorry. So what you want to do, make sure that you, when you use these different values, that you're using the same units so that they will cancel out. So eventually you do the calculation, times the temperature. So the temperature was 5 degrees, so that's 208 Kelvin, times the natural log of 2.25. So Kelvin goes away. We have what we're left with then is kilojoules per mole as our unit. And we substitute those into our equation, we end up with 4.60 kilojoules per mole. So we can calculate delta G if we know, or if we can calculate delta G naught, delta G standard, and if we have an equation provided, balanced equation, we have the concentrations, or if we have the partial pressures, we can use that instead of the concentrations if everything is in the gas phase. So what does this mean? Well, delta G here that we just calculated under these conditions, our delta G is positive, so delta G here is greater than 1. And what this means is that the reaction is non-spontaneous as written, which means it is spontaneous in the reverse direction. So what that means is, under these conditions, if we start off with these particular partial pressures, this reaction will actually go to the left. All right, remember delta G being positive suggests that the reaction is non-spontaneous going from left to right, which means it's spontaneous going from right to left. So by calculating delta G under these starting conditions, remember these are non-standard conditions now because our pressures are not 1 atmosphere, they're 2 and 2 and 3. We can calculate the delta G under those conditions and predict the direction of spontaneity, or in which direction the reaction will be spontaneous. If we change those conditions or those partial pressures, and now let's say we have the partial pressure of H2 of 2, of I2 of 2, and then HI of 1. If we substitute those into our Q expression as well, we end up with a Q of being of 0.25. And then if we substitute that into our equation, delta G equals delta G naught plus RT ln Q. That goes in here, the R and the T, they don't change. Delta G naught doesn't change. We end up with now a delta G value here that is negative 0.8 kilojoules per mole. So now we have a delta G of less than 1. And what that means, we have a negative delta G. The reactions will be spontaneous as written. So now by changing, if we instead started out with these partial pressures of the reactants and products, because this delta G ends up being negative over here, this suggests that this reaction will go as written from left to right. That's the spontaneous direction of that particular reaction. So we can manipulate the spontaneity of a reaction by changing the partial pressures of the reaction components. And by the same token, we can manipulate the spontaneity by changing the concentrations of the components of a reaction as well. So we've seen how to calculate delta G under non-standard conditions by using our equation. So we have our delta G is equal to delta G naught plus RT natural log of the reaction quotient Q. What we're going to do now is to assume we're going to take a look at a situation where we have equilibrium. So at equilibrium, this is defined as both the forward and the reverse reactions are happening at the same rate. So there's no net reaction occurring in either direction. And as a result, the concentrations of the reactants is constant, it's not changing. And also the concentration of the products are not changing either. So in this state, in this equilibrium state, we have Q, our reaction quotient, being equal to K, our equilibrium constant, right? Because that's what we have at equilibrium. What we also know at equilibrium, based on what we talked about previously, is the fact that at equilibrium, delta G, let me back up a second here, delta G is equal to 0. All right, so we have that up here. So by incorporating some of those equilibrium principles to our situation, we can simplify, scroll down a second, we can simplify our equation. At equilibrium, the reaction quotient Q is equal to the equilibrium constant K, and also delta G is equal to 0. So if we substitute delta G is equal to 0 over here, and if we substitute K there, what we end up with is 0 is equal to delta G naught plus RT ln of K. And if we rearrange this equation, there's a little bit of mental gymnastics on it, we end up with delta G naught, the standard Gibbs free energy, being equal to negative as constant times the Kelvin temperature times the natural log of the equilibrium constant. And that is an important relationship because it now relates the standard Gibbs free energy to our equilibrium constant for a particular reaction. And that is extremely important because what we are going to see then, just based on this equation, look at this general equation here, the larger the value of K is, so the larger K is the equilibrium constant, what we're going to see is that the more negative delta G naught is. Right, and that should make sense because we talked about that before. All right, the value for K, the size of K tells us where the equilibrium lies. If K is big, equilibrium lies to the right. That corresponds to a negative delta G naught value. Now, this is, like I said, is one of the more important equations of thermodynamics because what it allows us to do, it allows us to find the equilibrium constant for a reaction if we know the change in the time of Gibbs free energy, or vice versa. We can go backwards and forwards here and calculating either of these two things, if you know one of them. And we know what R is the gas constant, and we know what the temperature is that we're working under, as long as we convert it into the Kelvin temperature scale. So the two things you want to keep in mind when we start doing these calculations is as follows. And one of these you mentioned before. So the sign of delta G naught, the standard Gibbs free energy, tells us the same information as the magnitude of the equilibrium constant, K, Okay, and the other thing that we're going to see here now is that the sign of delta G, right, not the standard Gibbs reading, but the delta G for a reaction at any point along the reaction pathway tells us the same thing, or the same information as comparing the reaction quotient Q to the equilibrium constant K, right? So this, the sign of delta G tells us in which direction the reaction will proceed spontaneously to establish equilibrium, whereas the sign of delta G naught and the magnitude of K tells us where the equilibrium lies. Does it lie to the right? Does it lie to the left, etc. Okay, so it's not much of a difference in terms of the notation with that little degree sign there, the standard conditions. You can use one or the other. Delta G naught tells us where the equilibrium lies. Delta G tells us in which direction the reaction will proceed in order to establish equilibrium. So the table 15.3 in your text summarizes that information very well, and it relates K, natural log of K, and then the value for delta G naught, whether negative, positive, or zero, to tell you where that equilibrium lies. Let's remember, delta G naught gives you the same information as the magnitude of K. Let's take a look at an example of one of these. So using the data from the appendix, calculate the equilibrium constant, Kp, for the following reaction. So this is a reaction where water is turning into hydrogen and oxygen. Okay, and we're told that this is happening at 25 degrees Celsius, and our T here is 25 degrees C, and in Kelvin we add 273, so that's 298 Kelvin per T. All right, so a couple of things we can use here. Remember, when you have your equation, delta G naught equals negative RT natural log of K. This K could be any of those K values that we talked about previously. This could be Kc, it could be Kp, for example. Okay, so C in terms of concentration, it could be P or Kp in terms of partial pressures. It just depends on what type of system it is that we're looking at. In this case, we want to find Kp, the equilibrium constant in terms of the partial pressure. So we can use our equation. We have our delta G naught is equal to negative RT, natural log of Kp in this case. All right, so what we need to find here, can we just rearrange it really quick? We have our delta G naught divided by negative RT is equal to the natural log of Kp. So first of all, we need to find this side. Okay, so our delta G naught standard Gibbs free energy. We can calculate these using data tables in the appendix. And in order, again, for a delta G naught, that is simply the sum of the delta G of formation of the products minus the sum of the delta G naught of formation of the reactants. Yeah, we can look these up. For the products here, the products of hydrogen and oxygen, these are the elements in their standard state, so their delta G of formation would be 0. So 2 times hydrogen plus 1 times the oxygen minus, and then on the left side, we have 2 of the liquid waters. We look that up. That is 2 times, and then water is negative 237.2. Okay, these here, that's 0 for hydrogen and 0 for oxygen. So we have the 0, and then that's minus, and multiply these together. So that gives minus 474.4 kilojoules per mole. So then this ends up being our delta G naught here ends up being positive 474.4 kilojoules per mole. Okay. So again, we're using the the tables, the value from the tables to determine standard Gibbs free energy. That and then substituting in there. So we have now 474.4 kilojoules per mole divided by R, our gas constant, 8.314 times 10 to the negative 3 kilojoules per Kelvin mole. And then our temperature here is 298. Goes away. Moles go away, kilojoules go away, and then don't forget your sign. I've got the negative sign that we have in front. The negative of all of this is equal to the natural log of Kp. So then our Kp, we evaluate everything on this side here. So that ends up being, let's see, we have 4 divided by that times 298. That's going to give us negative 191.5 is equal to natural log of Kp. So then remember, natural log are to base e. So if I take e to the negative 191.5, that's going to be equal to our Kp value. Stick that in your calculator, and you end up with Kp being equal to 7 times 10 to the negative 84, right? So that is an incredibly small number, really small value for K. And what does the value for K, the magnitude of the value for K tell us? Well, because K here is a lot less than 1, so very, very, very small, that tells us then that the equilibrium lies to the left. Okay, and what that also tells us, because we found this up here, our delta G value is positive, and then this also confirms that the equilibrium lies to the left, because a positive value for delta G tells us the reaction as written is non-spontaneous. This tells us this water decomposing into hydrogen and oxygen does not happen spontaneously. And you know this from experience, right? The water you have sitting out on in a cup of water, in your house, at home, or wherever you have your cup of water, it doesn't decompose into hydrogen and oxygen on its own, right? So that makes sense. It makes intuitive sense. The numbers make sense. The fact that delta G is positive makes sense. The fact that the K value is so small makes sense as well. And it confirms what we found for delta G, or delta G naught.